Hello and welcome. Today we are tackling one of the most fascinating and, let's be honest, one of the weirdest ideas in all of science, quantum entanglement. But before we journey into the spooky, I've got to ask a quick favor. If you could just take a second to subscribe, ding that notification bell, hit the like button, and maybe drop a comment down below, it makes a huge difference and really helps us keep making these explainers for you. Okay, housekeeping done. Let's get into it. So we have to start here with this famous quote. When Albert Einstein called entanglement spooky action at a distance, he wasn't saying it was cool. Not at all. He was pointing out how absurd he thought it was. Back in 1935, he and a couple of colleagues, Podolsky and Rosen, brought this up as a thought experiment, basically to say, look, this can't be right. The theory of quantum mechanics must have a piece missing. He was convinced there had to be some deeper, hidden information that we just hadn't found yet. And that really gets to the core of the problem, right? This is the big question. Can two particles, separated by, well, any distance, even billions of light years, somehow influence each other instantly? I mean, that would seem to completely shatter the cosmic speed limit, the speed of light, which is the bedrock of our understanding of cause and effect. This is the mystery we're going to unravel today.
Okay, so to really wrap our heads around this, we need to start with the basics. Let's break down the rules of the quantum world that even make this strange connection possible. And it all begins with another idea that's pretty bizarre on its own.
And that idea is called superposition. The best way to think about it is like this. Imagine you flip a coin. While it's spinning in the air, before it lands, you could say it's in a state of both heads and tails at the same time. Superposition is kind of like that, but for real. A tiny particle, say an electron, has a property we call spin. And until you actually look at it, until you measure it, it isn't spin up or spin down. It's in a blurry, probabilistic fog of being both at once. It's the very act of measuring that forces the particle to snap into one definite state. All right, now hang on, because this is where it gets really weird. What if you could create two particles and link them together while they're in that state of superposition? Well, that's entanglement. Let's say we have two entangled photons. If you measure one and find its spin is up, you know in that exact same instant that its twin, even if it's on the other side of the galaxy, has a spin that's down. It's a perfect correlation, every single time. And it's not because they secretly agreed on their spins beforehand. No, the act of observing one instantaneously defines the reality of the other. And this leads us to this really controversial idea called non-locality. See, in our everyday world, everything is local. If you want to move a book, you have to touch it. If you want to talk to a friend, sound waves or radio signals have to travel between you. Something always has to cross the space from point A to point B. Non-locality throws that right out the window. It suggests a connection that just doesn't care about distance. Now here's a super important point. This doesn't mean we can send messages faster than light. You can't use this to call your friend on Mars. Why? Because the result you get when you measure your particle is always completely random. You can't force it to be spin up to send a 1 to your friend. But when you later compare your notes, you'll find that your random results and their random results are perfectly, mysteriously correlated.
This is the best way to understand the difference. Think about a pair of gloves. I put the left one in a box and the right one in another, and I mail them to opposite ends of the country. The second you open your box and see a left glove, you instantly know I have the right one. But there's no spooky action there, right? The information, which glove was which, was decided from the very beginning. That's a classical connection. Quantum entanglement is totally different. It's like having two potential gloves that aren't left or right, they're just gloves. It's only when you open one box and force it to become a left glove that the other one instantly becomes a right glove. The reality is created in the moment of observation.
So as you can imagine, this whole idea was so wild that for decades, physicists just argued about it. It was more philosophy than science. Was Einstein right and there was some hidden information, or was the universe truly this strange? Let's look at how experiments finally settled the debate. The story kicks off in 1935 with that EPR paradox we mentioned, Einstein's big objection. For about 30 years, it was just a stalemate. There was no way to actually test it. But then, in 1964, a physicist named John Bell came up with a genius mathematical test. Bell's theorem basically said, okay,
If the universe works the way Einstein thinks, with hidden information, then the correlations between these particles can only be so strong. But if quantum mechanics is right, the correlations will be even stronger. He gave us a line in the sand. And guess what? Starting in the 70s and getting more and more precise over the years, culminating in these amazing loophole-free tests since 2015, every single experiment has shown that the universe crosses that line. The spooky connection is real.
So what's the bottom line? The verdict is in, and it's a big one. Our common sense view of the world, what physicists call local realism, this idea that objects have their properties set in stone whether we're looking or not, and that nothing can travel faster than light, that's just not how reality works at the deepest level. The universe is fundamentally more connected and a whole lot stranger than our brains evolved to understand. But this isn't just some weird philosophical trivia. This spookiness is now becoming a tool. We're moving past just proving that it exists and are now actively figuring out how to use it. This strange quantum link is the foundation for a whole new wave of incredible technologies.
Seriously, this non-local connection is the engine driving the future. In quantum computers, entangled particles work together to create a massive computational power that could solve problems that are literally impossible for even the biggest supercomputers today. In quantum cryptography, you can use entangled particles to create encryption keys that are physically unbreakable. If a spy tries to intercept the key, the very act of looking at it breaks the entanglement, and you know you've been hacked. It's also letting us make measurements with unbelievable precision. And yes, quantum teleportation is a real thing. We're not beaming people around, but we can use entanglement to transfer the complete quantum information of a particle from one place to another instantly, without it ever traveling through the space in between.
And all of this, all this proof, all this new technology, it forces us back to those huge, fundamental questions. What does this actually tell us about the nature of reality itself?
Just stop and think about that for a second. If a property like spin doesn't even exist until a measurement is made, what does that mean for a reality out there that's independent of us, the observers? Does the moon only exist when you're looking at it? Well, not exactly, but it does challenge the idea that the universe is just a clockwork machine running on its own. It suggests that observation, consciousness maybe, plays a much more fundamental role than we ever imagined. And what does this do to our idea of space, of distance? If two particles can be connected in a way that ignores the space between them, maybe our whole concept of here and there is just a useful illusion for us big, slow creatures. We know these non-local connections are a fact of nature. The hard part now is figuring out how to fit that fact in with everything else we know, like Einstein's theory of relativity, which is built entirely on the idea of locality.
Which leaves us with this final, really mind-bending thought. If entanglement is real, and it is, it shows us that on the most fundamental level, the universe is not just a collection of separate individual things. It's a single, deeply interconnected whole. Maybe the idea that you and I and that star over there are separate objects, maybe that's the real illusion. Maybe, in a way we're only just beginning to grasp, it's all one system.
Thanks for watching. Please don't forget to subscribe, turn on the notification bell, like, and leave a comment to support the channel.